Welcome back to ECE 442-542. Tip-off will be now for class. I don't know when any other tip-off would be, so we'll tip off for class now. Just as a reminder, homework 6 is due Thursday, and next week is our third exam. Third exam is on the 16th, and we will have a review session a week from today is the plan, and that's consistent with what we've done for the other two exams in here. And exam number 3 material is now on D2L. And obviously maybe some of the material that is covered on homeworks assignments 5 and 6, which will be the content for exam number 3, you may not see that on old practice exams, but we'll try to discuss that in the review session. Essentially, the design by Ragazzini may not be on those old exams, those practice exams. And the other announcement that I need to make is that office hours for this Thursday, again, are shifted 2 hours later into the day, and they will be from 12:30 to 1:30. What I want to do today is develop more root locus rules, basically in the process of talking about proportional control. Seeing how we can select K or how we might get information about how to adjust that gain value to provide us with useful design information. I doubt we will get to the PI control strategy, but when you get to that problem on the homework, you already have enough material based on what we will cover today, even if we don't get to the PI control, because I've isolated it to where all you have is one adjustable parameter in the PI control strategy for the homework. Here's the proportional control that we've already talked about. Our controller, capital C of Z, is just a pure gain, K, in this unity output feedback configuration. The closed loop transfer function is Kg over 1 plus Kg. And we're interested in the closed loop dynamics, which are governed by the denominator of T sub C of Z, or we're interested in the roots of 1 plus K G of Z equaling 0. What can we do with that expression as we adjust this knob for the gain K? That's what we're interested in with proportional control. The root locus really works with that. The root locus tells us all the points in the z-plane that are possible closed-loop poles. Some of those might be unstable, but they're possible closed-loop poles. You may not want them, but that's what the root locus shows us. What you're hoping is that when you sketch this root locus, that you have simultaneously all of your branches of the root locus inside the unit circle at some value of gain K. Then you can stabilize your system. If you can find value or values of K in which all the branches of the root locus are simultaneously inside the unit circle, then you have, for that particular choice of poles and zeros of your system and controller, you have the ability to design a stable controller. That's what the root locus is trying to provide for us. As a summary, I'm just going to, again, scroll through some of these rules. Maybe we haven't stated them explicitly, but we've already worked through a couple of rules for the root locus. And here I'm going to talk about a generalized plant because that G bar, we might incorporate into that some of the pole and zero factors of our controller and factor out a gain K. If we can create an equation that looks like 1 plus K and then some rational expression, we're going to call that rational expression G bar of Z. And that G bar may be our plant. It may be a collection of our pieces of our controller, zero factors and pole factors. This is what I'm meaning by the generalized plant G bar. It might actually consist of, and there could be more than these two factors in this C bar of Z, but G bar represents everything in here except this gain K. So we're factoring that K out of everything in that forward path. That's how we will speak of this generalized plant G bar. If we're just using proportional control, these two zero and pole factors aren't in play, they don't exist, and G bar is simply G. Is that okay? I'm just trying to establish some terminology so that we can generalize these ideas for sketching a root locus, and it will allow us to include more than just when we have the plant. For example, we might have a PI controller which says we might have a zero factor and a denominator factor already selected, and we've factored out that K. Then we would include those two factors in with G to create our G bar and sketch the root locus for G bar. I think this will all become somewhat intuitive as we go through. I knew I would be writing too wide, but I hope this is okay. Here's rule number one, and you can see that, wow, it's an encyclopedia. It reads longer than it is. The first thing when you're sketching a root locus, what do? You identify your poles and zeros. You put the X's and O's, right? You start playing the game. You say, oh, a root locus, I'm playing a game. Let me put the X's and the O's down. And those X's and O's just correspond to G bar. You find the poles of G bar, you find the zeros, and you just mark those X's and O's down. Once you have the X's and the X's are the roots of D of Z, and the O's are the roots of N of Z equal to 0. We're going to have branches of our root locus equal to the number of open loop poles we have in G bar. So if we have 5 poles, we're going to have 5 branches of our root locus. And that's what we're starting with. We're saying the root locus branches begin on the open loop poles of G bar. So we start on the X's that we sketched, and we start moving towards the zeros. And now it's a good thing we've learned about infinite zeros, because the root locus branches go to our finite zeros and infinite zeros, if we have any. And how many infinite zeros do we have? Or where do they come from? The pole zero excess. So we find our pole zero excess, and that tells us how many zeros at infinity we have. We may have 1, we may have 2, we may have 3. If we had a pole zero excess of 3, we have 3 more poles than we have zeros. And we'll have then branches of our root locus going off to infinity on our root locus diagram. Rule 1, root locus branches begin on the open loop poles, and those branches end on the open loop zeros of G bar of Z, where the finite zeros of G bar of Z are the roots of N of Z, and so those branches terminate in this finite Z plane. The other branches actually go off to infinity in the Z plane. And those other branches, we have the number of those equal to the pole zero excess. That's rule 1, which we've already really talked about in a previous lecture. Rule 2, those X's and O's create, if they're on the real axis, they create segments on that real line. And we want to know are any of those segments actually, do they belong on our root locus? And one way to remember that, if we're using non-negative k's, is to just look at that line segment and say, are there an odd number of poles and zeros to the right of that segment? And if there are, then that segment is a part of the root locus. That comes about because of the phase angle condition, meaning G bar has to have an angle of minus 180, and we illustrated that last time by saying, oh, from this singularity, this pole, where's that line segment? Oh, it's behind me. So that one would have produced a minus 180, etc. But we can keep track of that by simply sketching our X's and O's and saying, for this line segment, do I have an odd number of poles and zeros to the right of that line segment? Now, let's get into doing this, applying this. Example 2 revisited. This is where I think we stopped last time. For this particular plant, G of Z, with proportional control, so this is all I have for G bar. G bar is actually G in this example. How many branches, or what's the number of root locus branches for this root locus? So we have 2 poles, 2 open loop poles, better be 2 branches. So we have 2 branches of the root locus. So now we can get some partial credit. We can say 2, right? We have 2 branches to keep track of. Which lines, well, the first thing we probably better do is put down our poles and zeros, shouldn't we? Our X's and O's. Where do those go on this Z-plane diagram? Where do I have X's and O's? What do I have at the origin, an X or an O? So I have an X at the origin, and that's due to that guy, isn't it? Do I have any others? I have another pole at 3 halves due to the Z minus 3 half factor. Now I have 3 real line segments. One from 3 halves all the way to plus infinity, another line segment from 0 to 3 halves. It's an ugly 3 halves, isn't it? And another line segment from 0 all the way to minus infinity. It's not much better. Are any of those line segments on the root locus? If I walked over to Z equal 2 and I said, what are the angle contributions of those 2 poles to the point Z equal 2, what would the angle be, the net angle? Does everybody see what I'm asking? If I'm over here at 2, what are the angles from each of those poles? 0. So I have nothing minus a 0 minus a 0. Those zeros add up to 0. That's not equal to minus 180. No points to the right of Z equal 3 halves are on the root locus. Now, what about this segment, line segment between the origin and 3 halves? First, if I was standing at 1, at Z equal 1, how many poles and zeros are to my right? 1. Is that even or odd? Is 1 even or odd? This gets really hard, doesn't it? That's odd. So that says, if we use rule number 2, that this segment better be on the root locus. And you can see that if you say, oh, what's the angle from, let's say, 3 halves over to 1, that goes through 180 degrees. The angle from the origin to 1 is 0. Their sum is minus 180. We subtract all the pole angles. And if we were living at minus 1, we have two 180s which sum to 360, and so there is no root locus point. That line segment from the origin to minus infinity does not belong to the root locus. Now, here's what could be confusing. How many branches did I sketch of the root locus? Trick question. Where do my branches begin? How many branches am I supposed to have? 2. But where do they begin? At the poles. And I have 2 poles. So I have actually 2 branches in that red line. I have one branch coming to the left from 3/2 as I crank up the knob K, and I have another branch starting at 0 and sliding towards 1 as I crank up the gain K. Meaning I now have a branch here and a branch there, and they're coming together to meet. Is that clear? So even though it looks like I have just one line segment, there's 2 branches there. That's where you could get confused, but you still have 2 branches there. Am I always stable for non-negative values of K? If this system is connected in a unity output feedback, negative unity output feedback configuration. Am I always stable? No, and that's what this root locus is supposed to be giving you in terms of an insight into the behavior. Stability is governed by the unit circle. Meaning initially, this little piece from 3/2 to 1, I'm not stable if one of my poles is out there. So I have to adjust the knob, crank up the gain K enough to get me to that point at 1. And that determines my lower limit of stability. So let's now look at the lower limit on K for stability. And really what we're doing is we are saying, here is our point that governs stability, and we want to get that branch that's probably starting at 3/2 over to that point z = 1. Now, how do we find the gain K to get us there? What's governing the behavior of our closed loop poles? Where do I want to go? This is our system that we're playing with. What governs the stability? What governs closed loop stability? This is your closed loop transfer function, isn't it? The denominator of that is what's influencing the closed loop stability. Let's look at that and see if we can use that to determine the value of K, our lower limit on stability. So if we look at the denominator of T sub C of Z, uh-oh, didn't like that. What in the world? Go away. They'll think advantage in a minute. I don't know if you saw that or not, but it's something to do with advantage. There's the equation that we're looking at. For this particular system, That gives rise to that equation. But we can now isolate the 1 by itself, or really we're identifying minus 1 if we subtract 1 from both sides. And the way to find k typically is to look at the magnitude condition. The magnitude condition says that the magnitude of that left-hand side has to equal the magnitude of minus 1, which is 1. We have two conditions, don't we, from that quantity equaling minus 1. We have a magnitude condition and an angle condition. This is really 1 at minus 180 degrees. So we can look at two different conditions for k over z times z minus 3/2. We have the magnitude condition that we are going to use to find k, which says then that we want the magnitude of k, z minus 3/2, to equal 1. That's the magnitude condition. And if we are dealing with k greater than or equal to 0, we don't really have to worry about the magnitude of k. It's going to be positive. So that allows us to say that k is the same, or k over the magnitude of the denominator factors equal 1. Let's just multiply both sides through by those denominator factors. And the magnitude of a product is the product of the magnitudes, so that we can start looking at the magnitudes of each of these individual factors. Meaning the magnitude condition now allows us to say that we have the magnitude of these two pieces, their product, determines the gain value k. But for the limit on stability, we want to know what gain value k happens when z is equal to what particular value. We want z to equal 1, don't we? So let's just evaluate that expression for k at that boundary of stability. Meaning we are now going to say k, when z is equal to 1, that will get us right to the stability boundary. Or we now have z minus 3/2, all evaluated at z equal 1. Again, this is pretty difficult mathematics. We have the magnitude of 1. We have the magnitude of 1 minus 3/2. Minus 1/2's magnitude is 1/2. We product those. We have a k value of 1/2, and that will now get us, so we crank up the gain k from 0 up to 1/2, and that will now allow us to get right to the stability boundary, right to the unit circle. So any value of k between 0 and 1/2 is going to give us an unstable system. So we need to crank up that gain to at least 1/2 to get us to a stable spot. What are the closed loop poles for that gain value, just as an aside? How would we find those? Do we have any kind of equation in play? Since this is a night, we tipped off at 5:30, we have to be playing a game, right? We have x's and o's. We have a root locus. Now, what's the equation that governs the closed loop poles? the denominator of t sub c of z, and that's just this 1 plus k g of z expression. We then have this 1 plus k g of z equals 0. But that's just 1 plus k over z, z minus 3 halves equals 0. And we now have a value of k. And what we need to look at is actually the numerator of that rational combination of terms. And that will give us the closed loop poles. The numerator then gives us z times z minus 3 halves plus k equals 0. And we're looking at k, a specific value of k equal to 1/2. We wanted to find what are the poles when k is equal to 1/2. That's the equation that we now have. But even without plugging that into the quadratic formula, we already know one of those roots, don't we? How did we pick k? We wanted to get right to z equal 1. So we know z equal 1 has to be one of those roots. If we didn't, we could just plug that into the quadratic formula and it's going to jump out at us, or we can just factor that if we wanted to. But by design, by the choice of k equal to 1/2, we know that this expression needs to factor into z minus 1, and hopefully now you can see what the other factor needs to be. So by the choice of k equal to 1/2, that helped us factor that, and now we have closed loop poles at 1 and 1/2. These are our closed loop poles with k equal to 1/2. Is that clear? So now the branches, we have 2. When we get to that box, we not only have a root there, but we have another root right there. We have 2 roots. We have 2 branches. The closed loop poles are moving towards each other. And we have one at z equal to 1, and the other one we didn't know where it was until we fixed k equal to 1/2, and then we found it. We said, oh, we're actually going exactly the same distance as we crank up the k, gain k. And that's not always the case. But in this case, with 2 poles and nothing else, they're moving at the same rate towards each other. Is that clear? At k equals 0, we have 1 at 0 and 1 at 3/2. We have an unstable system. We close the loop and we crank up the gain k. Now we crank it up to at least 1/2, and we'll be right there. We'll be right on the stability boundary, so we probably want to crank it up a little bit more than k equal to 1/2. What happens to the closed loop poles and the closed loop poles are really the root locus. That's why we're sketching the root locus, so we know where the closed loop poles are. What happens to those closed loop poles as k, the gain value, gets bigger or continues to increase? Well, if you really wanted to, if you were looking for something to do, you could say, well, I'm just going to pick a bigger k, a little bit bigger than a half. And then what would you do? So now I said, well, I don't know, make it an eighth bigger than a half, just for kicks. What equation would you plug that into to get the roots? What's the equation that you know is true that governs the closed loop poles of this particular system? They were given by this, which is the numerator of this, which we then rewrote in this form. And then we simply looked at a value of k equal to 1/2. This is now the polynomial that we're after. That's the equation. Now as we crank up that gain k, we want to know, how do the roots of this equation vary? What's going to happen to those? And is there a maximum value of that gain k when the closed loop poles, or when the roots, are still real? And by this point in the semester, you've probably learned to bring a coin to class, right? You can now pull out your coin and flip it. And it's not the pole 0 coin, is it? This is the yes/no coin. Is there a maximum value of k when the roots are still real? What am I asking? I'm now saying we have tried to look at this problem. We've sketched a root locus so far where these two branches, we've cranked up k to 1/2, and we have a pole at, or a root at 1/2 and another root at 1. Now we want to know, can we find the maximum value of gain k where those two just meet, where they just kiss? Make this a little bit more interesting. So we now have two poles that are meeting. What's the gain value to get them to that point of collision? How did you find maximums before? Derivatives, didn't you? We could do it numerically. We have the equation for k. If you wanted to, where did that go? There's our equation for k. We could just keep plugging in k values where, well, we're interested, can't remember where I'm at. We're interested in points between 0 and 3/2. We could put in a bunch of z values between 0 and 3/2 and see if we find a relative maximum in that k formula. And you could do that with your calculator, couldn't you? You know what's going to happen at 1. You're going to get a k of 1/2. Now put a z of 3/4 in there and see what happens. Put a z of 0.8 and see what happens. Put a z of 0.9 and see what happens to the k value. Do you find that you So I'm cranking up the knob, and right now I've cranked up the knob to 1/2. I keep cranking, and there's going to be a location, a z value, where they both are at the same point, and that's going to be a relative maximum between 0 and 3/2. We could find that analytically with your calculus, couldn't we? We could just say, well, we have the formula for k, or for our polynomial, there it is. Can we now say, well, let's look at the value? Well, maybe what we should do, where's our k expression? Right there. So now if we have k equal to z times z minus 3/2, what happens when we do this? This is now z squared minus 3/2 z. We take the derivative of that with respect to z, and we get 2z minus 3/2. And if we set that equal to 0, we get z is equal to 3/4. So that says that these are, and that makes sense for this particular choice of poles and zeros. We just had two poles, and they are now coming together, and they are going to collide at a value of z equal to 3/4. That's where the relative maximum occurs. And you could have found that numerically. So now we have real poles at z equal 3/4. And now what happens after those meet and we just get crazy and we crank up the gain k beyond the value that gets us there? Well, we could find the k that gets us there, couldn't we? K is equal to what? We have the value z equal to 3/4 when that hits a maximum. So now we have z at z equal 3/4. And what's the other? The other is 3/4 too, isn't it? So we have that squared. 9/16 is how much we have to crank it up. What if we get crazy and we go beyond 9/16? What's going to happen to our poles? They're not going to go through each other, are they? They're not going to just go whoops and sidestep each other. They're going to collide, and then they have to go off the real axis. So as we crank up, the real poles will meet at z equal 3/4 before leaving the real axis. And producing a complex conjugate pole pair. And we actually, in root locus terminology, we call that point where they leave the real line. So they kiss, now they have to break away. That's called a breakaway point. At the relative maximum, that's called a breakaway point in the root locus terminology. So a relative maximum occurs at the breakaway point. And sometimes we have the opposite. Sometimes they come back together and they collide at the real line, we call that a re-entry point, and that would be a relative minimum. But this is a relative maximum where they break away and they leave the real line. We can also have the opposite where they're now out there as complex conjugates and they come back in. That's now a re-entry point, and that's going to happen at a relative minimum, not a relative maximum of the gain k. So what do we have? We now have the gain, or we have two poles right there. And that is this z squared minus 3/2 z plus 3/4 squared. But if you didn't already have k calculated, you could say, well, my closed loop characteristic polynomial had that structure. My k was only in one place, and it was with the constant coefficient, and that would be another way of finding the k value instead of evaluating it from the k expression that we had before. So this is now 9/16, which is 1/2 plus a 16th. And a 16th is a half of 0.125. I remember what an eighth is. So this now is a half plus a half of 1/8, or point what? 0.5 plus 0.0625. Now if we crank up the gain k from 0 up to a half gets us right to the boundary. Then if we crank it up to 9/16, we end up with the gain k of 0.5625, and then we go complex after that value of k. So after k, and I just answered this question so you can put your coins back in. It's not even a yes/no question, but you can still put them back in your pocket. You don't want to leave them on the table. What happens as k increases beyond 9/16? And I've already answered that question, I hope. Here's our z-plane that we are sketching our root locus in. We know that we're living on that particular segment, and now we've figured out or determined that halfway between those two starting points is where we meet. And what's going to happen when they meet and we crank up the gain k? Which way are they going to move? Are they going to, whoops, I wanted, well, that's okay. Are they going to do that? Where this is going to go off that way and the other one's going to go that way? Are they going to be dizzy after they've collided and just kind of go crazy? Probably don't want to draw that on your exam. What do we know? Well, now let's remind ourselves of information that we have in play. Values on the root locus must satisfy 1 plus kg of z equals 0. But if we solve that for kg of z, that's -1, which is 1 at an angle of -180 degrees. So values on the root locus have to satisfy this equation for all values of gain k. And if k is positive or non-negative, then we need the angle of g of z to equal what? If we want the angle of this kg of z to be minus 180, and k is positive, its angle is 0, it's not going to contribute anything. We need the angle of g, all the poles and 0 factors in g, we need that to be minus 180 degrees. So the values on the root locus must satisfy the angle of g equals minus 180, and that implies the branches of the root locus, I'm getting tired and you're texting anyway, so just say RL, that's root locus. So now the branches of the root locus for this g of z those branches are actually going straight up and down. We have one branch going up, one branch going down. And they're at right angles, plus and minus 90 degrees. Where in the world did that come from? How many branches do we have? Let's see if we can sort of convince ourselves of that fact that we're now saying that the root locus, after these meet at 3/4, z equal to 3/4, we're saying that those red lines, one's going to go up and one's going to go down at right angles to the horizontal line. If we now sketch that here, what do I want to do? Let's now say that these are there, and halfway between, we're saying that one goes up and one goes down. Suppose we just select a hypothetical point right there. Then we know if this point is on the root locus, what do we know happens at that z value in the complex plane? What has to happen? I can't see if you're staring at me with blank stares or if you actually, I forgot my glasses, so I'll put them on. How can we verify that that box is actually on the root locus? We know that the angle of g has to be minus 180. So let's see if we can find or evaluate the angle of g at that box. So here's what I want to do. I want to look at the angle of g of z when z is right at that box. And that actually, if I look at that, I need to worry about this angle. Let me call that theta p1, and this angle, theta p sub 2. The angle from these 2 points, and if I had other poles and zeros in g of z, I would have to find their angle to that square. And I would add all of those up algebraically. The zeros would be positive. The poles are downstairs. We're subtracting their angles. I do not have any zeros, so I'm now subtracting this angle, theta p1, and I'm subtracting theta p2, and I hope that they both combine to end up giving me a net angle of minus 180 degrees, if that square belongs to the root locus. or lives on the root locus. I don't have any zeros, but I do have poles, so all of their angles are going to be subtracted. I have the angle due to the pole at the origin, and I want to evaluate that angle at the square. And I have the angle of the factor at, or the pole factor z minus 3/2, and I want to evaluate that at z equal to the square. But I hope that it's clear that by the way I've labeled this diagram, that this angle of the pole at the origin is just theta sub p1. It's measured with respect to the positive real line. That's just theta p1, and I'm going to subtract that. What's this angle of z minus 3/2? That factor. Theta sub p sub 2, I hope it's clear from geometry that that's 180 degrees less theta p1. That's theta sub p2. By the symmetry of that drawing, if it was drawn properly. Meaning, I can now say that this is minus theta p1 plus, and theta p2 is 180 degrees minus theta p1. Is that okay? So now I have theta p1 minus theta p1, and the only thing left is 180, and I'm subtracting that. That's 180 degrees. So at that square, and any other square that happens to live on that 90-degree branch, they're going to have an angle of minus 180. So all those points on that vertical line drawn straight up from 3/4. So this is a very important point. That point is z equal 3/4, which is the breakaway point. Any point on that 90-degree line is on the root locus. And we could do the same analysis going down. One branch goes up, one goes down. Questions on that? So now that's the complete root locus for that system. We have the real line segment, and then we have two branches. What's the pole zero excess for that particular system? 2. How many finite zeros did we have? We didn't have any. How many infinite zeros did we have? 2. So we expect two branches of our root locus to go off to infinity. One branch is going off at 90 degrees. The other one's going off at minus 90 degrees, or at 270. And those are our branches going off to infinity of the root locus. Yes? So if we actually had some zeros in this g of z, they are going to attract branches of the root locus. And some could bend the root locus into a different shape. And hopefully we'll get there in a quick example, so you can do your homework. But with this problem, we've cranked up the gain how much to get to a stable spot? 1/2. We needed k to be bigger than 1/2. Is there a limit? Is there a maximum value on k, or can we just keep going to infinity and remain stable? Now, Remember that picture, and now this is the question. Is there an upper limit on K for stability? All right, you will have to reach into your pocket and get that coin, maybe. This is a yes or no answer. Here's your picture. Here's the root locus. You now know this is true for all values of positive gain K. This is where your closed loop poles live. And are there certain values of K that you want to live with or select? Well, you've just found the lower limit. It's 1/2. Now, can we just keep going? We don't want to go outside the unit circle, do we? We're still inside the unit circle at 3/4, but if we cranked up the gain too much, we're going to leave the unit circle. And that's going to give us then this finite region of values of gain K for stability. Here's 1, here's -1. We now are needing to worry about this relative to that picture. The answer was yes. And now what we want to do is find the gain to get us to that triangle. And that's our upper limit. Do you have any ideas how we can do that? And that's going to have a twin down below, isn't it? We'll have a triangle here. It will have its conjugate where it just leaves the unit circle down below at the same conjugate location of the pole location. What's the real value of the pole? Z delta. Do we know anything about Z delta? It's 3/4, isn't it? So we know that this is 3/4 plus JY. We don't know what Y is, but we do know the real part. So we could write it in that form as a polynomial expression, couldn't we? But what else do we know? We know that if that triangle is on the unit circle and we only have those two triangles, what do we know about their quadratic expression? Do we know anything about it? And in particular, I'm asking, what's the constant coefficient of the roots that have those triangles as, well, I'm looking for the equation that has Z delta as roots. If we, how else can I say this? If I had two roots on that unit circle, what do I know? The radius is 1, isn't it? If the radius is 1, that's the constant value. That's the 1 squared. So we know that whatever comes out of the constant piece in this expression has to be, and we know what the linear piece is, but we know it's 1. And now we have enough information. We could have said, well, we also know that for this particular formula, or I'm sorry, for this particular system, we had the closed loop characteristic polynomial with z squared minus 3/2 z plus k. This is because of the unit circle. And so we really know what the gain is at the upper limit of stability by equating coefficients. So now we know that this system is stable between k values of 1/2 up to 1. What's the delta value? Well, we can multiply this one piece out. We know that z minus 3/4 squared plus y squared is equal to z squared minus twice 3/4 times z plus 3/4 squared plus y squared. And that is equal to z squared minus 3/2 z plus 1. So now we know 1 is equal to this combination of squared pieces. Or y is now equal to the square root of 1 minus 3/4 squared. And if we multiply all of that out, we get y is 0.6614. Or z delta is now 0.3/4. So it's 0.75 plus j 0.6614 with k equal to 1. And for stability, in this particular second order system, and we know a lot now about the behavior of our closed loop poles just from this root locus picture. We know how the closed loop poles change as we adjust this one parameter k. They only live on that root locus. So once you get up to 9/16, they have a real part of 3/4. And they'll always have that 3/4 real part as you crank up the gain k, but you don't want to crank up the gain k any more than 1 to remain stable. Is that clear? And that keeps you inside the unit circle. Yes? So the maximum value of k was a relative maximum. So the question was, I thought we just found a maximum k. And you're correct, we did find a maximum k, but that was a relative maximum to try to find where on the real line do these points break away. And this is not really a maximum value of k. K goes off to infinity, but the maximum value of k to maintain stability, to stay inside the unit circle, is 1. So somebody could say, oh, design that controller and put k equal to 2. You're going to leave, aren't you, the room and say, go ahead, you can use k equal 2, but I'm not going to be present. Because what's going to happen? It's unstable. It'll start burning up, possibly. It will go unbounded for a bounded input. So this is the range of k for stability. So we're talking about a lot of different maximums, aren't we? We had a value of k, we had a sort of a minimum value of k for stability, that was 1/2. We had a maximum value of k for stability, that was 1, and we had a relative maximum on the real line to get us to where they met, and that was 9/16, if I'm remembering right. And then we crank it up a little bit beyond that, which was the 0.5625, up to 1, And now, if somebody said, oh, I want a particular percent overshoot, now what do? You might want to find the angle, but intuitively, you're thinking percent overshoot, it's some heart, it's a logarithmic spiral, and you'll find that zeta value, and where does that intersect that vertical line? That's the value of the poles for that percent overshoot, or that's the location of the poles. They would still have a real value of 3/4, and their imaginary piece would be dependent on what they said the percent overshoot needed to be. Is that clear? All right, now, bummer. I want to give you some more stuff, and I don't... All right, that was example 2. Let's look at example 4. Maybe this lecture is not linear, but that's okay. Maybe I'll come back and give you example 3 some other time. Suppose somebody gives you a g of z equaling k z minus 1/2, z minus 1, z minus 2. Now, can you help me start the root locus for this? And just think of it as a game, right? And if it's a game, then you need to know, where do I put my x's and o's? That will give you a couple of points, right, of partial credit on the exam. Where do you put, do we have any o's? We have something at 1/2, don't we? So there's 1/2. Do we have any x's? Now, how many different real line segments do we have for in total? We've now subdivided our real line into different line segments. One line segment is at z equal 2 all the way up to plus infinity. There's 1. We have another segment between 1 and 2. There's 2. We have another segment between 1/2 and 1. That's 3. We have a fourth segment between 1/2 and minus infinity. We have 4 different real line segments that are potential places for the root locus to live. Can you help me shade where the root locus is on the real axis? Is the root locus to the right of 2? Is it between 1 and 2? Coin? Is a root locus segment between 1 and 2? There's an odd number of poles and zeros to the right, isn't there? How many root locus branches do I have? How many open loop poles do I have? 2. I have 2 root locus branches. That's actually 2 branches, isn't it? One starts at 2, and the other starts at 1, and they start running towards each other. Yes? Is this line segment between 1/2 and 1 on the root locus? So now you stand at 3/4 and you look to your right and you say, let me count the number of singularities. Pole at 1, a pole at 2. 2. Even or odd? 2. That's not odd, so it must not be on the root locus. All right, so that's not going to get shaded red. We move to the left of 1/2. We go to the origin as a possible point, and we say, how many poles and zeros are to my right? 3. 3 is odd. Oh boy, that's supposed to all be on the real line. There are my, but those are my real root locus segments. Uh-oh. Now what? What do we know is going to happen between 1 and 2? Question? So now the question is, why is there I think this is the question, why is there a root locus segment between 1 and 2? Is that the question? Anybody want to answer? If I just looked at a point, let's say 3/2, and now I said, what are the angles that get me to 3/2 from all of those poles and zeros? What's the angle contributed by the pole at 2 to 3/2? It's 180. What's the angle from the pole at 1 to 3/2? 0. What's the angle from 1/2 to 3/2? 0. So now I have 0 minus 0 minus 180. So any point between 1 and 2 will have an angle of minus 180. Or the quickest way to do that is say, let me stand at any point between 1 and 2 and look to the right. Is there an odd number of poles and zeros to my right? Yes. So that segment, that whole segment is on the root locus. Now if I move to 3/4, that's not true anymore, is it? Because I have an even number of poles and zeros to my right. If I go to -1 and I look to the right, I go, oh, there's 3 of you guys. I must belong on the root locus. Now what happens? Besides me getting nervous. What happens? Why is there a segment to the left of 1/2 all the way to minus infinity? Is that the question? Because if you look at any point on that portion, on that real line segment, the angle to that point will be a multiple of minus 180. I have 180 from 2. I have 180 from the pole at 1. I have 180 from the angle at, or the 0 at 1/2. So I have 180 minus 180 minus 180. So the net is minus 180. Any point between z equal 1/2 and minus infinity has that for its angle. Does that help? And if I stand here, I see 1, 2, 3, an odd number of poles and zeros to my right. Yes, so now we look at each of these possible real axis segments, and we look to the right and we say, is there an odd number of poles and zeros to the right? And if there are, then that's on the root locus. That's the quick way to sketch these. The long way is to measure the angles from each singularity and add them up algebraically. Now, what's going to happen? What's going to happen between 1 and 2? We'll have a relative maximum, won't we? That little character. We're going to have a relative maximum. They're going to meet, aren't they, between 1 and 2, and what are they going to do? Okay, so what's the pole zero excess here? 1. How many branches at infinity of the root locus do I have? How many zeros at infinity do I have? How many fingers am I still holding up? 1. The pole zero excess is 1. I have one infinite zero. I have one branch going off to infinity. That's that guy going off to minus infinity. So everything else has to somehow be playing in this finite z-plane. So I have two branches that are going to leave between 1 and 2. They're going to break away. Those two branches are going to come back and re-enter between 1/2 and minus infinity somewhere. One's going to go to that finite 0 at 1/2. The other one's going to go off to minus infinity as you crank up the game. Now, you can find the relative maximum here, and once you do, it's actually going to form, because of this 2 poles, 1 0, this 0 is going to form the center of a circle. And the radius is going to be dependent on that breakaway point. Now you can just get out your compass, draw your circle, and there's your re-entry point. Is there any possibility of being stable in this system? Both branches, I only have 2 branches. You want both branches to simultaneously be inside the unit circle. And if you sketched the unit circle, and my drawing is probably terrible, but you have this, whoops. So we'll enter, and then we'll leave, won't we? So we'll enter here, and we'll leave. One guy will leave there. 2 will enter. See how symmetric it is? But that's supposed to be the same. It's conjugate, symmetric. And the triangle, the other one might be in there. But once one goes out, we've lost stability. I'll have to pick up at this point. But if you really want to do this, you could enter, you know how to enter that transfer function in MATLAB. Let me just bore you here with one more thing. So let's say that we have this transfer function, GD. We say we need the numerator, which was z minus 1/2. We had 2 poles, which I'm going to multiply those together and get z squared minus 3z plus 2. Is that correct? So now this is 1 minus 3, 2. And if I don't know the sample period, I just enter a minus 1 for my TF function. But now all I have to do to sketch the root locus, you should know that MATLAB has a command, rlocus, GD, and it'll sketch the root locus. And if you need to find points, you could say, you know what, I'm going to look for one point, that's the one, a graphical input. And this will give you crosshairs in MATLAB, and you can put those crosshairs where the root locus intersects the unit circle and click on your mouse, and it'll give you the point where that happens. And you can use that point to figure out the gain. I may give you an intermediate lecture between now and Wednesday. I don't know. We'll see. But this should get you started with the homework. Enjoy the rest of the game.